Alright, so here's chapter 4.3 on logarithmic functions, and I'm doing this straight out of the book. I tried to do that earlier with the smartboard software on a tablet in my office, and it just didn't work at all. I mean, I got it somehow done, but this might be a whole lot easier. So anyway, definition of a logarithm. I explain that the logarithm looks for the exponent of a base that results then in the answer. For example, down here, forget about the equals 2 here. Logarithm base 3 of 9 looks for the exponent for the 3 to come up with 9. So 3 to the second power would be 9. Hence, there you can see it. And that actually explains what they're trying to do here, which is, I'm just using their example. Let me jump to the third example here. Example C here. So log base 2 of 1/4. Well, there's a 4 there, so it's probably 2 to the second power is 4, but that's not 1/4. Again, this is actually the result. Well, how do I make 4 into 1/4? I do it 1 over 4, respectively 4 to the negative 1. That's where the negative comes in. So if you rewrite this as 2 to the negative 2, you will come up with 1/4, because it's 2 to the second is 4, and the negative then in the exponent inverts it. And here, log base 5 of the square root of 5. How come is that 1/2? Well, the square root of 5 is 5 to the 1/2, and then actually, as you find it in the next section, you can pull the 1/2 to the front. This is actually the easiest way, and you actually have left log 5 of 5, which is 1, 5 to the first power, but you have the 1/2 in the front. So let's see what they did in this example here. So here, log base 3, 9, 2, exactly the way I explained it. To what power must 3 be raised? Part C here, similar to the way I explained it. So to what power must 2 be raised? We use 1/4. Well, and I said you need the 2, and then you need the negative to put in the denominator. Note that this, and then part B, note that the square root of number is the same as raising a number to 1/2 power. To what power must 5 be raised to produce the square root? And I explained it a little bit different. I already took something from the next section. All right, let's see. Check it out. Rework example 1. Log base 3 of 27. Well, I'm looking for 3 to the what? 3 to the third is 27. So the answer is 3, and that's how I would write it then. 3 to the third equals 27. All right, let's skip this one. Let's go to example 2. 4 to the 0 power is obviously 1. And you can see it already at the bottom of the screen. How would I rewrite that? Well, my base is 4, so I'm going to rewrite it as log base 4 of the numbers 1. That's my result. And you can see that here. So log 4 base 1. What is the exponent for the base 4 in order to give me the 1? Well, 4 to the 0 power is 1. So again, what I'm looking for over here is the exponent, the power of it. Here, this one is the result that I want to get out of it, and this one here is the base. I'm going to skip this one here, but I do like the 6 to the 1/3. And again, in the smartboard software, that was just the toughest to write the square root symbol and then copy and paste and superscripts and subscripts. It was just almost impossible. Anyway, so what is the logarithm of the cube root of 6 with respect to base 6? So they actually don't want us to evaluate that. They just want us to rewrite that one here. So the base is 6. The power is 1/3. Sorry, I didn't highlight it all. There it is. Highlight it all. And the result is actually the strange-looking cube root of 6, which is probably in the neighborhood of, how is it, 1.8, something like that. Anyway, and then what you rewrite it for is the log base 6 right here of the result, and that is 1/3. And again, borrowing from the next section, the cube root of 6 is actually the exponent 1/3, which you can pull to the front, and then you have log base 6 of 6 is 1, and 1/3 in the front. There you go. Okay, a couple more examples here. So 4 to the third equals 64. So we would write log base 4 of 64 equals the power 3. Okay. Let's see, valuing logarithms move out using your calculator. So log base 5, 125. You're looking for the exponent. 5 to the what is 125. So 5 times 5 times 5. So the answer is 3. Log base 5, 125 is 3. Okay, to get from 10 to 100, 10 to the second power is 100. So the answer must be 2, but it's in the denominator. So negative 2 is the answer. Log base a4 of a to the 4th. I can pull the 4, again, that's one of the properties from the next section. I can pull the 4 to the front, and I have log base a to the of a. So I'm looking a to the first power equals a, which is 1, of course. But I also have the 4 in the front, so the answer will be 4. A to the 4th to give me a to the 4th, that kind of thing. All right. Let's see what the next example gives us. Solving an equation involving a logarithm. So use the definition to find the value of x. Well, that's what I've been doing all this time. So log base 4, 16 equals x. Well, 4 to the second power, so the answer would have to be 2. And so what they do is they rewrite it here. 4x to the 16 as the exponential equation. And then they're just looking at it. So they're actually not really solving it. I just say, hey, just look at it and figure out what that is. By the way, if you did that on a calculator, it's a little bit harder. That's what they're going to show us soon here with the change of base formula. Because if you have 4 to the x power equals 15 instead, ooh, what are you going to do then? You cannot guess anymore. All right, the other one here, log base 3x equals negative 2. You rewrite it as an exponential equation, so 3 to the negative 2 equals x. So 3 to the second is 9, but because of the negative, comes into a denominator, so the answer is 1/9. Solve the equation log base 5x equals 3, so that would be 5 to the third power equals x, which we already had, that is 125. So here is the natural log and the common log. That's the one that's based on base 10. And why are they important? Well, the base 10 logarithm log, I pulled that up, is a convenient way to express large numbers. Base 10 logarithm of a number is roughly the number of digits of that number, for example. So if I take 1 trillion, which is 10 to the 12, well, the 12, the power, that's the logarithm of 10 to the 12. So I can just look, instead of writing that huge number out, I can just say, hey, the exponent is 12, so take the logarithm of it to get that exponent. And because it's not necessarily 1 million, but it could be 2.3 trillion, I'm sorry, trillion, 2.3 trillion, or 1,465 billion, and so on. So you don't necessarily get integers when you take that logarithm. The natural log, its importance is based on, well, logarithms are used to solve for half-life, decay constant, or unknown time and exponential decay problems, also growth, exponential growth. And of course, it is the inverse function of the exponential function based on Euler's constant E. So the natural log is totally linked to Euler's constant E. And I found this one here from Numberphile, this British program, I think, and I posted it within our lecture, and here's just 20 seconds from that video.
If you write it in terms of E, then the maths becomes much simpler. Because if you don't write it in terms of E, you get lots of nasty constants, and the maths is really messy. If you're not trying to deliberately avoid using E, you're making it hard for yourself. It's the natural language of growth. And of course...
So what I meant to show here is, especially where he said that, and by the way, he was referring to calculus. I skipped that part, watch the video, it's pretty good, talking about gradients and areas and the e to the x function being the only one that does that. And so he talks about that, hey, once it gets to calculus, if you try to avoid the e to the x function, which also means if you try to avoid the natural log function, then you make it a whole lot harder for yourself. So this one here becomes very important. By the way, one of the first things you learn in calculus is what is the derivative of this one here. And then later on, how do you get that as an integral, and so on. All right, so let's look at these here. Valuing common and natural logarithms. Log of 10,000. Well, just count the zeros. 4. So the answer is 4. And this, of course, is base 10. So when we only write log we are referring to log base 10. So because 10 to the 4th power is 10,000, again, we're looking for the exponent. Natural log e to the 1/2. Well, that again, from the next section, pull the 1/2 to the front when you have then 1/2 times ln of e. So ln base e of e is 1. And that means the 1/2 is the answer. And look what I'm using. I'm using the graphing calculator. So I'm just going to type it in here, ln of e to the 1/2. It's optional to close the parentheses, but I might as well do it. There it is. And the answer is 1/2, 0.5. Because it's the same as 1/2, I can pull that 1/2 to the front. That's the properties of logarithms. Oops, and then I chose the wrong one. I meant to choose ln first and then e. And so now I have no more exponent here. So I'm just going to write 1, or I could write e if I found it somewhere. So that should be, by definition, 1 times the 1/2 here in the front is 0.5. And again, if I just use ln of e itself, then I get simply 1. All right, going to skip this part over here. All right, let's go on. I'm going to skip this one here. And here's the change of base formula. So a calculator is only going to give us the 10 log and the natural log. So base 10 or base e 2.71. Remember that one we had just a couple of pages ago, this one right here, 4 to the x equals 16, well, we can easily guess that x equals 2, that's the power, which of course we get through the logarithms. But what if we have 4 to the x equals 15? Well, it ought to be close to 2, maybe 1.9, maybe 1.8. But this is the formula that will give us that result. So what I'm going to do that on the calculator, I would type in log, which would be the log 10 of the result, 16, divided by, and I know I actually was supposed to use 15, but just show you first what happens when we're changing the base when we already know the result. So log 16 over log 4 should be 2. And there it is. Okay, so again, now we're going to have 15 instead. I'm going to do this. Just not going to type it all again, but just fix the 16 to the 15. And sure enough, 1.95. And again, I can check that. 4 to the 1.95. If I abbreviate this a little bit here, you will see that, of course, I'm only going to come close, very close to it, right? It's back to 15 rounded, but that's because I truncated my answer. All right. So next thing we're going to do is we're going to get to graphing. And oh yeah, I should actually show this because I just showed you the 10 logarithm. If I did the same thing that I just did with the natural log, so natural log of 15 divided by natural log of 4, either way works for the change of base. I come up with the same answer, 1.95. And again, when I do 4 to the answer, in fact, I do take the answer right now, I come up with exactly 15, as I expected. So here's the graphing, and they give us a table here as an example. And notice the numbers they choose here, because the logarithm makes really small numbers and really large numbers. It squeezes it together, and so for really large numbers you get kind of small integers, and for really tiny numbers you get reasonable small negative integers. So you have 10 to the negative 10, which is a tiny, tiny number, but you get a negative 10 when you take the log with respect to base 10 of that. All right, so here's the graphing. The logarithmic curves have a certain look to them. They kind of look similar to the exponentials, but then not quite, right? Because it's actually a origin mirror of it. So the exponential would actually turn up here, which means that they're, of course, inverse functions of each other. And while the exponential has a horizontal asymptote, the any kind of logarithm has a vertical asymptote. And the domain is going to be 0 to infinity, because you cannot plug in a number less than 0 there is no way you can get to that result with very few exceptions. For example, you could get, for example, -8. Well, to the base -2, that actually would be -2 to the third power, right? That would actually work, but usually it doesn't. And then actually, if you change the calculator to complex numbers, actually, then you make it kind of work. It's interesting. So as far as the domain and the range are concerned, they actually turned around from the exponential, obviously, because they're inverse functions of each other. This one here actually looks like a negative. Just put a negative from the logarithm. Here they explain it differently. It's as if your base is less than 1, but still larger than 0. So 0.3, for example, or 0.5. I can show you that in a moment in Desmos. So here we're just going to take the normal logarithm, and I think I'm going to make this smaller so that we are able to see more. Let's see, yeah, that's it. Okay, so y equals simply log of x, and there it is, right? And if I zoom in, I don't know, it doesn't make it a whole lot better. Notice the second one actually looked like this, right? Just flipped on the x-axis. Now, how can that be? Well, we will find out in the next chapter, in the next section, that that negative that I have in front of the log, of course, is a -1. Well, I can take the -1 back inside, but when I take it back inside, it becomes this. It becomes an exponent, -1. And notice that is actually then the same thing. And of course, log x to the -1 is the same as log of 1 over x. So, whoops, I meant to put the parentheses there, all the same. That's where that comes from. So it's actually from a property from the next section. All right, let's go back to lecture. Okay, now there's actually too much on here. I'll make this bigger again. There, that's a little better. All right. And I just discussed this one here, them being inverse functions of each other. All right, let's see what they have here. Oh, they have examples. Let's do those. But it's not going to be too bad. So I'm going to do log 3. Oh, 3 log 2. Log of x minus 1, it says. And then I divide that change of base formula, log 2. Because Desmos 2 will only do the natural log or the 10 log. And you can see in the book that's indeed what it is. Right here, that was the first one that I graphed, and here's the second one that I graphed. Okay, basic applications for logarithmic functions. So here's earthquakes in the Richter scale. Intensities of earthquakes are so large that in order to compare them, you have to multiply by a factor 1,000 or 10,000, and they're hard to compare. So they're actually pulled back down to just numbers we can handle. So you have heard of these big earthquakes, which are on the Richter scale 8.6. But what it really means, it's 10 to the 8.6. So it's kind of almost close to 1 billion or so in intensity. Or here it says, right here, 6.5. Well, that actually means the intensity is 10 to the 6.5. Now notice that 6.5 is larger than 5.4 in comparison. But it's not 1.1 times more. No, it's about 10 times more. Because, again, 10 to the 6.5 is somewhere in the millions, while 10 to the 5.4 is somewhere in the hundreds of thousands. Factor 10 less, and you can see the results here, 3 million something, and here it is 251,000, so approximately 10 times more. Other applications, by the way, I'm going to show you the distance of planets here in a moment, but from a different point of view. But other applications you will find in astronomy actually too, for the brightness of stars, but we will also find them in chemistry for the pH of a solution, so that's how basic it is or how acidic it is. We will find it for loudness as well. And all right, so I'm going to show this planet example that I had in mind. So here's a table of the planets. These are the distances of the planets. I know Pluto's in there. If it's a planet or not, I don't care. So here are the distances. This is in millions of kilometers, and here's the orbital period in days. And then in astronomers, we like to actually put them in years. That makes total sense, right? So Earth needs exactly 1 year to orbit. Jupiter almost 12 years. Uranus needs 84 years, and so on. And Mercury even just needs a quarter of a year, 3 months to orbit. You can see that right here, 88 days. These are distances as in multiples of Earth's distance. Earth's distance being 149.6 million kilometers, which is 93 million miles on average. So it's what we call one astronomical unit, and Mercury is appreciably closer, and so is Venus, and the others are further away. Well, you can see, so Pluto, for example, is almost 40 times further away than the Earth is from the Sun. And so you can see that obviously there's a relation between these. Now, when I graph these, I just copied them, so I'm going to get this. And there we go, and there's a nice graph here, and it looks like it's going up here. It's definitely not exponential, but it is a power relationship between them, but it's hard to see what it actually is. So instead, what I'm going to do is I'm going to graph their logarithms. So I'm going to get rid of these data, and instead what I'm going to type in here, I'm going to just pull this down just a little bit, and I'm going to type in here equals, take the logarithm of the 0.39, there we go, and then also take the logarithm of the 0.24, so it's right next to it, and then just copy this down here, or pull it down, and it takes the logarithm of everything there. And then I just can take these here, again, copy them, put them back into Excel, I'm sorry, into decimals. And okay, that's a little small here, so I'm going to hit the plus button, and there it is. Wow, nice straight relationship when I write down the logarithms of those numbers. So I'm looking for a line here. Well, a line is simply going to be y is proportional to slope times x plus an intercept, and it's a perfect relationship among the planets. So the b here really is actually truly zero. I mean, it's really, really close. But the slope here is 1.49899. Not a coincidence that this is close to 1.5, because it is actually exactly 1.5. And that, the slope of this line here, is actually the exponent for the relationship, so that the period and the distance, I'm just writing this one here, so period takes to, or distance versus period, I'm going to write it like this, is in a relationship of 1.5, which is also 3 over 2, right? I don't know if it's going to calculate that. Ooh, okay, it didn't do that, but all right, 3 over 2, it's probably going to do March again. Oh well, okay, so 3 over 2, but what that then means for us, for astronomers, is that d goes with the third power, and the period, so distance goes with the third power, and the period goes with the second power. So cube and square, and 3 over 2, of course, is that 1.5. So this is where logarithms come into in order to see those data for the planets somewhat better, that, wow, there's a nice relationship. All right, that was the lecture for the section 4.3.